Hi there. Today we are going to see four matrices of linear regression. The first one, mean squared error. So how this mean squared error is calculated? So it is calculated by calculating the distance between each data point and the best fit line that have been arrived after training the model and squaring them up and then summing them all and then dividing it by the number of samples. So basically, when we look at its formula, it says that yi minus yi hat. So yi is the actual data point, it is the ground truth, and yi hat is the predicted by the model, that is lying on this best fit line. So the difference between the two is squared, and this is calculated for each data point and then it is summed up, and the result is then divided by n, that is the number of samples. So this is how the mean squared error is calculated. It is also called as sum of squared error. If we talk of its range, so its range starts from 0 and it can go anywhere up to plus infinity. Moving on to our next metric, that is mean absolute error. So mean absolute error is more or less the same as mean squared error that we just saw. The major difference is that the distance, that is a difference between the yi and the yi hat that is predicted and the actual y point, is not squared, it has taken the absolute value. So if the difference is coming out to be negative, then that is adjusted and that is made positive, and then it is summed up and then eventually it is divided by n number of samples. So this is how mean absolute error is calculated, and its range is again from 0 to anything up to infinity. Now coming on to a very important metric, that is R square. So R square is basically calculated with the formula 1 minus a factor, and this factor has a numerator which is sum of squared error and denominator as total sum of squared. Now sum of squared error we just saw in mean squared error. It is this distance between the yi, that is the ground truth, and the predicted y, that is y hat, and squaring it up and summing it for all the data points, and then we get sum of squared error. And in denominator we have yi minus y bar whole square summation up to n, that is we are going to take the difference between the actual value, that is the ground truth value of y, and the average of all the data points in the sample, that is in the test data, on which we are applying this r square to get the information. So this is that y bar, this is the average of all yi's, and that is difference is being calculated squared for all data points, and this is how we get the denominator, and this factor is then subtracted by 1. And if I talk of the range, so it can have range between minus infinity to plus 1. So in general, a model that is giving us a value of r square close to 1 is a very good fit, and anything which is giving us value something close to 0 or less than that is a bad fit. So this is how we can have evaluation for our model using r square. Another very important metric is adjusted r square. Now adjusted r square is something which is always less than the r square. It is a refined form of r square, so that we want to know whether with increase in the dimension, when r square increases, does it really has an impact on the model. So for example, I have a variable which is increasing the R square. So I just want to know whether that variable is truly increasing the accuracy of the model, or it's based on the formula it is increasing the R square value but not increasing the actual accuracy of the model. So in that scenario we use adjusted R square. So the formula for adjusted R square is 1 minus a factor, and what that factor is, it has 1 minus R square, the R square that we just calculated, multiplied by n minus 1. Now this n minus 1 is nothing but the number of samples in the test data on which we are applying the adjusted R square, and this divided by n minus p minus 1. So here n we already know it is the number of samples on the test data, and p is the number of independent variables or independent features that we have in our model. So this is how the adjusted R square is calculated, and its range is always less than the R square. So that is the key thing over here. Now let us jump onto the demo part, how we can calculate these in real time in real world scenarios. So I have a data set already been procured from the Seaborn library, that is tips data, and I have created a linear model. So I'm not going to go through this right now. We are just directly go to the metrics part, and we'll be calculating these 4 matrices on our model which has already been trained. So here I have taken my target variable as tip, and my independent features are all the rest of the features. So I'm going to predict how much tip is being given for a particular table. Okay, so that is our use case. So I have already trained my model. Let's just execute it once more. And so I have imported the sklearn metrics, and I'm importing these libraries: mean squared error, R square, and mean absolute error. So here I'm not importing any adjusted R square library. We will be calculating it ourselves with our own custom code. So here I'm going to import the mean squared error function. So I'm going to call that function, and inside the parenthesis the first parameter that I'm going to give is y_test, and then second parameter I'm going to give is y_predict. Always guys, remember we have to give the first parameter as y_test and the second parameter as y_predict. Otherwise the predictions of the parameter value will not be correct. This is the correct way of passing the parameter, and then I execute it. So I get mean squared error as 1.505. Now let us calculate the mean absolute error. So I'll call this function mean absolute error, and inside the parentheses I will pass y_test first, then y_predict, and then I will execute it, and I get 0.90 as the mean absolute error. Now we are going to calculate our R square. So it is also pretty simple. Since we have already imported that library, we will call this function, and we will pass these parameters as y_test first and y_predict, and then I'm going to execute it. I get 0.43. So we see that our mean squared error is 1.5, which just looks pretty decent, and mean absolute also 0.9. But based on the values, I see that the R square score is not so good. So that means we need to improve the model with hyperparametric tuning or some more feature engineering, or we need to do some other modifications, or altogether utilize any other model to improve the accuracy of the model. So let us talk about the adjusted R square. So if you remember that we just talked about the formula to calculate adjusted R square, and we are not going to call any particular library for that. We are going to create our own code for that. So I give a name adjusted underscore R square is equals to, and it is 1 minus, and then it is inside the parenthesis 1 minus R square that we just calculated in the above, and then I'm going to multiply it by the number of samples in the test data, that is y-test, that is on which we are going to apply our model testing, that is on which we are going to apply this R square KPI. So this is the n value in it, and I am subtracting it with 1, and then I'm dividing this particular factor with the n, that is again the number of samples in the test data minus, if you remember, there was a value p, which is the nothing but number of independent variables, and then I'm going to get that number with xtest dot shape 1 would give me the number of independent variables minus 1. Now this should be also completely in one bracket, because we want to subtract this factor of numerator and denominator with 1, and this will give us the adjusted R square. So let's see what is our adjusted R square. So we get a adjusted R square of 0.32, which is not so good, which is close to 0. So this is how we can know that how good our model is performing, and then we can improvise from there on, but we get the answers right. We also saw that the R square is more than the adjusted R square, that is adjusted R square is always slightly less than the R square. So that's all folks in this video. Just to summarize, we saw by formula and basic understanding of what are the matrices for a regression model, that is mean squared error, mean absolute error, R square score and adjusted R square. And then we also saw their formulae and also how we can calculate it programmatically using the sklearn library. So this is it in this video. I'll see you in the next video. Do subscribe to my channel. See you.